A very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering. Today's topic is problems on links. Right? Firstly, coming to the first problem, calculate the velocity of the tip of two link planar RR manipulator arm, which is shown in the figure. Right, this is the figure which is being seen where we have a number of links and joints. Right, as you can see in the figure, this is the fixed position, and this is the y-axis, this is the z-axis, and this is the x-axis. Right, x, y, and z-axis. Now, to this particular fixed link, we have a link being joined where this is one of the joint, right, and at this joint we have at this particular position, right, where these particular links and joints are moving with an angle θ1 and θ2. Right, now we need to calculate the velocity of these particular two links, that is link 1 and link 2. Right, we need to calculate the velocity of the two links which are planar to the RR manipulator. So firstly, we need to calculate at the point P. Right, we need to calculate at the point P. So when we are calculating at the point P of the two links, the RR manipulator, which is shown in the figure, determines that the x-axis, when we come across the x-axis is being given as x is equal to L1 cos θ1 plus L2 cos θ2. Right, whereas y is being given as L1 sin θ1 plus L2 sin θ1 plus θ2. So in this particular equational form, we will be calculating the velocity where x-axis is being taken as L1 cos θ1 plus L2 cos θ1 plus θ2, whereas y-axis is being taken as L1 sin θ1 plus L2 sin of θ1 plus θ2. Right? Now, as I've said you, when we need to calculate the velocity with respect to the x-axis, the x is equal to minus L1 sin θ1, right, minus L2 sin of θ1 plus θ2. This is into θ1 dot minus into θ1 dot plus θ2 dot. Right, so this is how we write the velocity when we come across the velocity components at the point P, that is the positional equation. Whereas when we take the y-axis y dot is equal to L1 cos θ1 into θ1 dot plus L2 cos of θ1 plus θ2 into θ1 dot plus θ2 dot. So this is how we write x dot and y dot for the velocity in the x direction. So the magnitude of the velocity, that is the magnitude of the velocity at the point, at the tip P, can be calculated as the square of x dot square plus y dot square, that is v is equal to root of x dot square plus y dot square. So when we are considering this particular equation, we can calculate θ1 dot and θ2, that is the velocity of the tip at the point P on the angular velocity, that is θ1 and θ2 dot. The link will be L1 and L2 at a length of L1 and L2. Right? By substituting these values of θ1, θ2, or the values of θ1 dot and θ2 dot, we can compute the specific velocity of the overall magnitude of the particular equation. right? That is, when we are considering, this is a general calculation which is to be done, that how we find out the velocity when different links are being given. So we will be considering x and y axis with respect to the velocities and the angles, and then with respect to the velocity components, that is with respect to the angular velocities, we will be calculating x dot and y dot with respect to the x-axis and the y-axis, right? So here the velocity, angular velocity, will be written as square root of x dot square plus y dot square, where we are calculating theta 1, theta 2 and theta 1 dot and theta 2 dot, that is the specific velocity of the component for the overall magnitude of the velocity. So this is how we calculate the velocities when two links are given, right? Moving on to the second problem, that is, a moving frame 1 is represented by the following rotation matrix R, where alpha is the angle of rotation of the frame 1 with respect to the base frame. If alpha is a function of time, find the angular velocity for frame 1. That is, he is asking us to find out the angular velocity for frame 1. Now, the rotation matrix, we are considering it as 1 to 0, right? The rotation matrix with respect to the frame 1 is being written as R1 to 0, that is frame 1 with respect to 0 base. So that we will be writing as the matrix cos alpha minus sin alpha 0, sin alpha, cos alpha and 0, 0, 0, 1. In this particular matrix form, we will be writing the rotational matrix, where alpha is nothing but the angle for the frame, angle of rotation for the frame 1. And since the alpha is the function of time, we need to we are interested in finding the angular velocity of the frame 1, that is omega, right? How do we represent angular velocity? With omega. Since already alpha is being determined, that is, alpha is nothing but the function of time, we need to find out the angular velocity with respect to the frame 1, that is the actual given question. So here, since the rotational matrix already we know, right, with respect to x-axis, we have written it here. Now, with respect to the angular velocity, the rotational matrix will be taken as R1 of 0 dot R1 0 into omega. This is how we write the problem with respect to the angular velocity. Now, since the angular velocity is nothing but the symmetric matrix, right, for the vector omega, so the matrix will be represented as R1 0 dot is equal to minus sin alpha into alpha dot or minus cos alpha into alpha dot into 0. And this is cos alpha alpha dot, sin alpha alpha dot, 0. 0, 0 and 0. This is how we write the rotational matrix for the angular velocity. Now, using the relation, so this is omega, right? Now, using this particular relation, that is R1 0 dot is equal to R1 0 into omega. Using this particular equation, first we need to find out omega. What is omega? How we write a matrix for omega. So omega has been written as omega is equal to 0 with respect to the z-axis, that is minus omega z. With respect to the y-axis, it is omega y. And omega z 0 minus omega x minus omega y, omega x of 0. So this is how we write the matrix for the omega, right? So here, now we need to solve the angular velocity for omega with respect to the rotational matrix, that is this. So what is this particular matrix which we are taking here? It is nothing but minus sin alpha into alpha dot or minus cos alpha into alpha dot or 0, right? Or this will become cos alpha alpha dot minus sin alpha alpha dot or 0, and this is 0 and 0, 0. So this is how we write the rotational matrix, right? Now, so now with respect to the angular velocity, this is written as R1 into omega, which will be equal to cos alpha minus sin alpha 0 or sin alpha cos alpha 0, 0, 0 and 1 into 0. What is the omega? Minus omega z, right? Minus omega z 0, omega y or omega z 0 minus omega x minus omega y, omega x and 0. Now we need to multiply these particular two matrices in order to get the rotational matrix with respect to the angular velocity. So that we will be writing it as minus sin alpha omega 2 minus cos alpha omega 2 cos alpha omega y plus sin alpha omega x, right? So next, cos alpha omega z minus sin alpha omega z sin alpha omega y minus cos alpha omega x, and this will become 0, 0 and 0. So this is how we write the matrix for rotation with respect to the angular velocity. Now what will the final equation become? Yes, when we are considering this, what will the final equation become? Equating the equation 1 and 2, minus cos alpha dot is equal to minus cos alpha wz, where we get wz is equal to alpha dot, or therefore the angular velocity, right? Therefore the angular velocity omega is equal to omega x, omega y and omega z, which will be equal to 0, 0 and omega alpha dot, right? That is omega is equal to alpha dot into z along the z axis, right? Along the z axis we are getting this particular equation, right? That is when we are equating, when we are equating the equation 1 and 2, we are getting minus cos alpha dot, which will be equal to minus cos alpha. What is alpha dot? It is nothing but wz. So the angular velocity for the omega x, omega y, omega z will be equal to 0, 0 and alpha dot along the x axis when we are considering the z axis, or when we are considering the z axis, right? Next, moving on to the third problem. So, derive the equation of motion for a single link manipulator given the mass and length of the link. That is, the mass and length of the link is being given. We need to derive the equation of motion for a single link manipulator. So, how will we do that? In order to derive the equation of motion for a single link manipulator, we will use the Lagrangian approach. Right? With the help of the Lagrangian approach, we will standardize the method in the classical derivation equation system. That is, the angle of the link, that is it will be equal to theta t, which is nothing but the function of the time, or we will be considering the gravity, that is acceleration due to gravity, or we will be considering the mass m, right? Considering these particular three for a simple pendulum, when we consider a simple pendulum, right, for that particular simple pendulum, we will be considering the mass, we will be considering the gravity, acceleration due to gravity, and we will be considering the function of the time. So, considering all these particular constraints, we need to assume that the link is connected to a pivot point. Right, we need to assume that the link is being connected to a pivot point, and the kinetic energy will be taken as T. Right, the kinetic energy will be taken as T, and the velocity is being written as velocity is equal to L by 2 into theta dot. That is, for since this is angular velocity, we have taken theta dot, and T, that is the kinetic energy. Kinetic energy, we have represented it by the help of T. So, kinetic energy T is being taken as 1 by 2 mv square we all know. What is v here? 1 by 2 m of L by 2 into theta dot of whole square, which is nothing but 1 by 8 ml square theta dot square, right? That is nothing but the kinetic energy. So the velocity, the angular, with respect to the angular velocity, v is equal to L by 2 into theta dot, and the kinetic energy, we all know it is the formula of half mv square. So v is already been determined as L by 2 into theta dot. So that when we are substituting, we are getting the kinetic energy as 1 by 8 m L square into theta dot square. Now moving on to the potential energy. So how will we determine the potential energy with respect to the height from the center of the mass, right? With respect to the height from the center of the mass, h is being written as L by 2 cos theta, right? H is being written as L by 2 cos theta, where v is nothing but mgh. Right, for the potential energy, we are considering it as a V, and we know the formula for potential energy is that mass into gravity into height, that is mgh. Now all the values we have, right? M g into h value is L by 2 cos theta, right, which is nothing but the potential energy V. Now when we are considering the Lagrangian length or the Lagrangian equation, now we need to take the difference between the kinetic energy minus potential energy, right? The Lagrangian equation is nothing but the difference between the kinetic energy and the potential energy. So what is the kinetic energy which we have got? It is nothing but 1 by 8 ml square theta dot square, and the potential energy is mgl square cos theta. So we have written Lagrangian equation as L is equal to 1 by 8 ml square theta dot square minus mg L by 2 cos theta, right? Now when we move to the equation, like Euler's Lagrangian equation, right? When we are moving to the Euler Lagrangian equation, d by dt into dou L by dou theta, right? D by dt into dou L by dou theta minus dou L by dou theta is equal to 0. This is the equation, Euler's Lagrangian equation. So as per this particular Euler's Lagrangian equation, we need to do the partial differentiation, partial derivation, right, for Lagrangian with respect to theta dot, right? Now for this particular equation, we need to do the partial derivation for Lagrangian with respect to the theta dot. So how will we do that? How will we get that? Dou L by dou theta dot is equal to dou L is equal to dou by dou theta dot into 1 by 8 ml square theta dot square. Now when we have got this, what will the equation become? 1 by 4 ml square theta dot square. That is the equation which we are getting for dou L by dou theta dot when we are doing a partial derivation for Lagrangian with respect to theta dot. Now when we come across with respect to time, when we come across with respect to time derivation for dou L by dou theta, we will be writing it as d by d theta into dou L by dou theta dot is equal to d by d theta into 1 by 4 ml square theta dot. Right, this is this particular equation, 1 by 4 ml square into theta dot. Now what will we get here? It is 1 by 4 ml square theta dot dot, right? That is with respect to the time derivation. When we come across with respect to the time derivation, this will be equation which we will be getting. Now when we do a partial derivation, when we do a partial derivation of Lagrangian with respect to theta, what will we get? That is dou L by dou theta is equal to dou by dou theta into minus mg L by 2 cos theta. We will be getting this particular equation. Now when we are getting that, what will the final result become? 1 by 2 mgl sin theta. This will be the final partial derivation of the Lagrangian with respect to the theta. Right? So after that, we need to find out the equation of motion. We need to find out equation of motion. So how will we find out the equation of motion? It is nothing but 1 by 4 ml square theta dot dot minus 1 by 2 mgl sin theta is equal to 0. So this is how we write the equation of motion, that is 1 by 4 ml square theta dot dot minus 1 by 2 mgl sin theta is equal to 0. So that further when we solve, we will be getting 1 by 4 ml square theta dot dot plus 1 by 2 mgl sin theta, which is equal to 0. This overall we will be getting it as theta dot dot plus 2g by L sin theta is equal to 0. So this is the final equation of motion which we will be getting with respect to the Lagrangian equation. Right? That is, first we need to find out the kinetic energy, then we need to find out the potential energy, and then we need to write down the equation of Lagrangian, that is the difference between the kinetic energy and the potential energy. Then with the help of the Euler's Lagrangian equation, with the help of the partial derivation for the Lagrangian with respect to the theta dot, we will be getting equation number 1. After that, with respect to the time derivation, we will be getting equation number 2. And further doing the partial derivation for Lagrangian with respect to theta, we will be getting equation 3. And when we are writing the equation of motion for the overall content, then we will be getting the overall equation of motion. Right? We will be getting the overall equation of motion. Right? So this is about, these are the references which we have gone through. And this is about, these are the problems which we have dealt today, and hope you have understood regarding the links and regarding the Lagrangian equation problems. Right? So this is all for today. Signing off for today, Dr. G. Hima Bindu. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.